We're going to give an example of how we can apply Gauss's law and the conditions for electrostatic equilibrium to find the electric field and charge for a particular example. So in this example, you're given that there's a spherical conductor with a radius A. It's a solid piece of conductor, and they told you that they put an extra charge 2q. And then there's empty space. This is empty space. And then there's another spherical conductor, but it's a shell. It has an inner radius B and it has an outer radius C. And they said that they put an extra amount of charge on this shell minus Q. And the question is, what is the electric field everywhere in space, and what is the charge, how is this charge minus Q distributed on the spherical shell? So the first question we want to think about, where is the charge located on the inner and outer conductors? Of course, when charge plus 2q is placed, extra charge is placed on the conductor, or the conductor has extra charge of plus 2q, the charge has to be on the surface in equilibrium. We took this before. So the charge on the inner sphere is on the surface. And for the spherical shell, what we know is that the charge has to be on the surface. So there could be some of the charge on the outer surface and some of the charge on the inner surface. We don't know how much Q inner is. This charge is Q inner. And we don't know how much Q outer is. This is Q outer. But we do know that when you add them, the total charge on this outer conductor, the spherical shell conductor, has to be minus Q. That was part of the given in the problem. So all we know is that the sum is minus Q, but we don't know the value of Q inner and the value of Q outer. This is what we have to find in the problem. So let's start for finding the electric field for the region where R is less than A. If you're inside this conductor, what is the electric field? We know that in any conductor in equilibrium, the electric field has to be 0. So the answer is very simple, between 0 and A. Okay, what about between A and B in this region? This is empty space. There's nothing there. It's completely empty. What's the electric field in this region? Well, we can always apply Gauss's law. Now, what shape Gaussian surface would we use and where would we put it? So clearly we're going to make a spherical shell. This dotted circle represents a cross-section of a spherical shell. It's a sphere. And we want to apply Gauss's law using this spherical shell. So this is the left-hand side of Gauss's law, integration of E dot dA. Now from the symmetry of the problem, as we did with many other problems for spherical symmetry, the direction of the electric field is in the same direction as the area vector at every location on the surface. So the dot product E dot dA becomes EdA. And second of all, since the electric field is constant from symmetry, we don't know what the value is, but we know it's the same value if you get it here, or you get it here, or you get it here. It's the same magnitude. So we can take E outside of the integration, so it becomes E times integration of dA. And integration of dA is just the total surface area of this dotted spherical shell that has a radius r. That means the area is 4 pi r squared. And so the left-hand side of Gauss's law just becomes E times 4 pi r squared. Okay, what about the right-hand side of Gauss's law? The right-hand side of Gauss's law is asking what's the charge, the total charge inside this Gaussian sphere. So let's look inside the Gaussian sphere and see how much charge is there. We can see that the charge is plus 2q. So we know that the charge inside is plus 2q. So the left-hand side of Gauss's law, we found it's this. The right-hand side of Gauss's law, we found it's this. So now we can write the electric field by dividing by 4 pi r squared. And we get the electric field in the region between A and B turns out to be 2q over 4 pi epsilon naught r squared. This is the same electric field as if there was a point charge at the center of the whole problem with a value 2q. Okay, what about in the region between B and C, in this region? This region is inside a conductor. We know that inside a conductor in equilibrium, the electric field has to be zero. So the electric field is zero in this region. Okay, what about for R bigger than C? If I want to go outside all the conductors. So I'm going to make a spherical Gaussian shell with the radius R, but now R is bigger than C. And I want to apply Gauss's law for this spherical shell. So the same thing exactly as before. The direction between E and area vector is in the same direction, so the angle is zero, so E dot dA becomes E dA. And second, from symmetry, if you get the electric field here, or you get the electric field here, or you get the electric field here, anywhere on the spherical shell, the magnitude of it is the same everywhere, even though I don't know the value of it, but I know it's the same. So I can take E outside of the integration. So you're left with integration of dA. Integration of dA is the total area of the spherical shell, which is 4 pi r squared. So the left-hand side of Gauss's law is exactly the same as before. What about the right-hand side? What's Q inside? What's the charge inside this dotted spherical shell? Well, if you go inside, we said that the total charge on this spherical shell, this one, the conducting shell, is minus Q. And then the total charge on this conducting sphere is plus 2Q. So that means the total charge inside the dotted spherical shell is 2Q minus Q. And so you get the total charge inside is just Q. So the left-hand side of Gauss's law is just E times 4 pi r squared. And the right-hand side of Gauss's law is Q over epsilon naught. So we can then say that the electric field is just Q over 4 pi epsilon naught r squared, which is the same as the electric field due to a point charge with value Q, located at the center of the problem. Okay, so the next question we wanted to ask is what is the charge on the inner surface, this charge, and what's the charge on the outer surface, this charge. I put the charge to be negative here and positive here because I know the answer, but you don't have to if you don't want to. You could just illustrate it as some charge but without putting the sign, and here some charge without putting the sign. But obviously, because there's positive charge here, it'll attract negative charges on this inner surface. So intuitively this will be the answer, but you don't have to really think about it this way. We can derive it exactly from scratch. So can you think how we could use Gauss's law to find the charges on the inner and outer surfaces of this conducting shell? Think about it for a couple of minutes and then continue. So one way to do, we can do that by making a Gaussian surface, a spherical shell, but the spherical shell is located inside the conductor. So why do we put the Gaussian surface inside the conductor? Because the electric field inside the conductor in equilibrium is zero. That means the left-hand side of Gauss's law is zero. That means that the charge inside the Gaussian surface has to be zero. And how does that help us solve the problem? Well, what is the charge inside this dotted Gaussian spherical shell? If you go inside, you'll see that part of the charge that's inside is this one, which we called Q inner, and part of it is this 2Q. So actually the charge inside is basically Q inner plus 2Q. So we know from Gauss's law that Q inner plus 2Q is zero. That means we can get Q inner. So Q inner turns out to be minus 2Q. And that's again why I wrote it as minus here, negative charge, because it's exactly equal and opposite to the charge on the inner conducting surface. Now that we know Q inner, and we know also from before that Q inner plus Q outer is minus Q, that was given in the problem, then we can get Q outer. So we can just plug Q inner to be minus 2Q, and then take it over here to be plus 2Q. Plus 2Q minus Q is Q, so you get Q outer is equal to plus Q. And that's again the reason why in the beginning I put the charge on the outer surface to be the plus Q. Okay, so this is a summary of everything in the problem. The charge on the inner surface, spherical surface is 2Q given, and we just proved that the charge on the inner surface of the spherical shell is minus 2Q, and the charge on the outer spherical shell surface is plus Q. And to check, we can always add these two. They should give you minus q, because it was given in the problem that the sum of these two was minus q. They didn't tell us how much was on the inner surface and the outer surface. This is what we proved in the problem. And then the electric field between A and B, it goes like 2q over 4 pi epsilon naught r squared. The electric field after C goes like q over 4 pi epsilon naught r squared. And that's the summary of the problem.